Hello, it's Lee, back in the lab again. I'm just setting up the equipment now to test these two RF meters here, these the GQ EMF-390 and the TENMARS TM-195 meters, which I found on Amazon. Now, when you're testing devices like this, there are a few important things you need to consider. The first is that you want to have a very controlled environment because you want to be able to maybe do some tests over a period of hours or maybe even days. So you want to make sure that external influences are kept to a minimum. That is normally quite hard to do it in a typical house or an apartment where you might live, or especially outside, of course. Luckily, I live in a very strange old place here, and I have a basement, but there's also a lower basement which looks like a kind of thing you might have used for some kind of bomb shelter perhaps during World War II. It is completely underground and it's surrounded by thick concrete walls and sort of quite a thick concrete ceiling which is reinforced, so there's sort of rebar in there. And there's only one small door into it. There's no mains cabling in there apart from some lights. And I took these meters in there and I've taken some other readings in there. And it is a very quiet RF environment. There's no Wi-Fi in there, there's no mobile phone signals. You can't even get an FM or AM radio signal. It's really good. But just to make sure it's even better, I've put some shielding over the wooden door and made sure that's grounded. So it is now a really quiet environment. The next thing you need is a reliable signal source, a reliable transmitter. So what I'm using for that is this software-defined radio here. This is a Lime. You can see my messy bench here. You can see this is a Lime SDR. This software-defined radio goes from basically 1 megahertz up to 3.8 gigahertz, which is absolutely ideal because that is the current range of most things that transmit around the UK, apart from 5.8 gig Wi-Fi. But it includes most of the current 5G spectrum, and certainly all the 2, 3 and 4G spectrum, and of course 2.4 gigahertz Wi-Fi. So I'll be using this. This can transmit a signal at any of those bands at 1 milliwatt. So we'll have a 1 milliwatt transmit signal. So that's absolutely perfect. This is what I've used for some previous tests when we tested some antenna systems. Put that to one side. That is driven by a laptop. So the laptop does all the processing and tells it what to transmit. The laptop, of course, could be transmitting all sorts of nasty rubbish which will affect our readings. So we want to keep the laptop away from here, or at least away from our receivers, but it uses USB 3 and long USB 3 cables again could emit some RF, so we don't really want to use those. And I haven't got the money or the time to make a big long really well shielded cable. So the only thing to do is to put the software-defined radio and the laptop, which is quite a big laptop here, and this laptop here, into a shielded case, run it off batteries, and use that in our RF quiet room to transmit our test signal. Luckily, I've got some of these old boxes here. There we are, some of these big old boxes. Put the SDR here. So what I'm going to do is put this connector here in the middle of here, and I will make some kind of gizmo so we can change the antennas here according to what frequency we're going to be using, and then inside the box that will be connected to the software-defined radio transmitter. So I'll have to set the thing up to transmit, close the lid, make sure the whole thing is grounded properly. There's some good ground there, there's some gas or some kind of water pipe in there which should be fine, and then that will be our reference transmitter in the basement, which we'll use to test those RF meters. So here we go. So here we have our transmitter now built. It's in a fairly RF proof case. It's got an antenna on top. this antenna is currently a quarter wave at 868 megahertz, so that'll be one of our test frequencies. Inside is a software-defined radio here, and a laptop which will control the software-defined radio. So that is pretty much ready to go. All I need to do is make sure the laptop's charged up, because currently it is not at all charged up, and I'll make some antennas for our test frequencies. Now, the meter we're testing, well, the two meters we're testing, this one here, this is the TENMARS meter, and we've got the GQ EMF thing here. This one claims to go to 10 gigahertz, which I doubt somehow, but we'll have a look. We'll try and test that. This goes to 3.5 gigahertz. So let's define our test frequencies. Find a bit of scrap paper here somewhere. Here we are. That'll do. And that is all sorts of nonsense on, but that'll do fine. Here we are. So let's define some test frequencies. And what I'll do is, down in the little RF proof room, which I'll show you in a minute, it's sort of that kind of shape. It was originally, I built it to be a recording studio with a friend of mine, and it had sort of padded walls, so soundproof walls, insulation, and in the middle here there is a big soundproof wall with some double glazing in. There's a little door here which is gone, and there's a door here. There's another door there. So what I've done is that door is now being covered with some RF shielding. The rest is completely underground. What I think I'll do is we'll put the transmitter, put the transmitter here, and put the receiver here. Receiver, of course, will be these devices here. We'll have them both going at once. And I will put a camera by the receivers here, so I can monitor what they're doing without being in the same space and potentially affecting the readings. So I will not be present when they're taking their readings here. They do have a way of recording data, so that might be another option as well, rather than putting a camera there. The transmit frequencies, so we're going to try actually this is tuned for 869 megahertz, so we go to 869 megahertz. And I think we'll go for some popular ones. We'll go 433, 144. So that covers the two ham radio bands. That covers the sort of low power lighting control band as used in the lighting control systems such as, oh gosh, where are they? I've got them around here somewhere. I don't know, they're around here somewhere. But that covers those. And then let's go to 1800 megahertz. That's a popular mobile phone band, and we'll do 2.4 gigahertz for Wi-Fi and 3.5 gigahertz, which is at the limit of this device, and that covers the top of it, around about the top of the current 5G frequencies in the UK. So let's just note some things down here. So that's sort of VHF ham radio, and that's UHF ham radio. That's the long range, low power stuff. That I don't know. It's probably mostly sort of 3G, GSM, 4G stuff. There's also sort of 4G, 3G round it, and GSM 800, 900 megahertz. That's covered by that quite nicely. 2.4, of course, is our Wi-Fi band, and 3.5 is 5G. So that covers the kind of things that you probably want to be detecting with these meters, and the other meters on the way. So, yeah. So this is the inner sanctum of the basement. Let's turn the light on here. And here we have the Scout stores. There's all the Scout kit here. And this is where all the tents and other kit happens to be. Looking at this, I might need to slightly revise where we put some of the kit. But that's okay. But here, there's no mobile phone signal, there's no Wi-Fi signal, there's no radio signal. It's covered in all sorts of equipment here, so there'll be reflections off the walls and off the concrete ceiling here, but it's all going to be scattered around everywhere, so there'll be lots of exciting stuff happening, so it should be absolutely fine for taking some signal readings here. What I'll do though, I've got my tape measure, and we want to put the
The transmitter, well, you know what I'll do, I'll put the transmitter down here at this end, and we'll put the receiver just about there by the window, and that should help us out, I think, a bit. That'll be absolutely fine. But I need to take some measurements. Let's put the camera somewhere and work out how big this is going to be. So we need to do some mathematics now to calculate the theory behind what we're going to do, and we want to do this because what I want to do is to work out what, in theory, our meters, both the orange one and the grey one, are going to be picking up, so we can see if they're actually anywhere near what we think they should be. So to work these things out, let's first draw out what our test lab is going to look like. So it's roughly oblongish like that, isn't it? Round about like that. And we're going to have our transmitter about here. And the antenna is in the centre there. That is the big silver box we made earlier. And what I'll do is I'll put a little sort of shelf thing here made out of plastic. And we'll put the two test receivers on here. So there'll be one here with a little ball at the end, and the other one will be there right next to it. The distance between the transmit antenna and the receivers is exactly 300 centimeters. And what I'll do is I'll measure out a bit of string, and I'll sort of sellotape it to here and tape it down to here, so we make sure we get that exact 3 meters for everything we test in this lab here. What I'll also do is make sure that nothing is disturbed in the lab area, so whatever we put there later on, if I have another device in a week or so, I'll make sure that it's in exactly the same lab environment. What we need to do then is work out, if we have a transmitter here with the antenna we have here, what is the RF power density going to be down here? And working out RF power density is really easy. It's a formula like this. So power density equals the power of the transmitter times the gain of the transmit antenna, and that is divided by 4 times pi times radius squared. So we need to work out a few things here because we've got to plug some values into this formula. The r squared is the radius, that's this distance here, so we know what radius is. It's going to be 300 centimeters. The power of the transmitter, well, we're going to be using a Lime SDR. Its max transmit power is 10 dBm. We don't want to run it at 10 dBm for too much, because it's going to get hot, and also if we run it at its max limit, then potentially we get some interference and a nasty transmit signal, and we want to try and keep it nice and clean if we can do. So the power of the transmitter is going to be 8 dBm. And we need to work out what that is in milliwatts as well. The gain of the transmit antenna, we're using a quarter wave monopole, so quarter wave ground plane antenna, and the gain of a quarter wave ground plane antenna over an isotropic antenna, which is a sort of theoretical ball antenna that transmits in all directions, is about 2.8 decibels. So 2.8 dBi gain. So we've got our figures now. What I'll do is I won't do it calculator here. I'll plug it into the online RF calculator, just because then you can do it at home and you can make sure that I'm not cheating you and doing anything silly. So let's switch over to that now. There we are. Actually, before we do that, we need to make sure of one really important thing. We need to make sure that our receivers, these ones here, will actually be able to receive the signal. And the spec for the TM-195, let me move back to that camera a second. The spec of the TM-195, this one here, is it will receive down to, looks like 0.001 microwatts per meter squared. That's 0.1 microwatts per meter squared. So 0.001 microwatts per centimeter squared. So let's write that down, shall we? So we don't forget that. So it's so the TM-195, it's going to be 0.1 microwatts per meter squared, and that's going to be 0.001 microwatts per centimeter squared. Okay, the spec for the GQ EMF meter is not in the manual, but I noticed earlier they got a link here to the full user guide, which you just saw. So let's flip over to that full user guide now and work out what the minimum receive signal for that device is going to be. And here we are. It is, so resolution, the range is 0.02 microwatts. So EM-390 is 0.02 microwatts per meter squared. Okay, so the minimum signal that the orange thing needs is 0.1 microwatts per meter squared, and the minimum that the EMF-390 needs is going to be 0.02 microwatts per meter squared. So this one is a bit more sensitive, which is quite nice. Also, I said earlier that there's no specs for this thing here about what it actually does and what the sort of margins of error are going to be. It's actually in this document here, so that's fine. We can be happy with that now, and I'll have a bit of a read of that later on and just make sure that we're not doing anything untowards. So now we need to calculate what our power density is going to be at our receiving station 3 meters away from the transmitter, and for that we're going to use the super duper everything RF calculator. We're transmitting at 8 dBm. Let me just do that in front of your eyes so we're not going to do anything dodgy there as well. So we need to convert dBm to watts convert, and I'll do it online right here for you, just so you can do it at home as well and make sure that nothing funny is happening. Where is my favourite one? It's disappeared. Oh, here we are. It's the top result, which I missed. So we're transmitting 8 dBm, and that is 0.0063 watts at 6.3 milliwatts. Here we are, 6.3 milliwatts into the antenna. The antenna gain is 2.8 dB. Look at that for yourself. It's a quarter wave monopole ground plane antenna, 2.8 dB gain over an isotropic antenna. And we are 300 centimeters, that's 3 meters away from the transmitter. Calculate, and we have 1.062 to the minus 5 milliwatts per centimeter squared. We need to convert that, of course, over to watts per square meter, microwatts per square meter. And let me do that now. So, you know, actually, let's just do it on paper, sure. It'll be easier. So the RF power density down here at the receiver is going to be 1.062 to the minus 5 milliwatts per centimeter squared, and the receive requirements for the two receivers is 0.1 microwatts per meter squared and 0.02 microwatts per meter squared for the other device. Let's convert our figure here into that. So it's going to be 106.2 microwatts per meter squared. So that looks absolutely fine. So I think we have a good chance of receiving a signal on the devices here and seeing if they work. Now, what will happen, of course, is we'll take these devices down into the basement, and they will already be receiving some signals. And we need to take that into account because there'll be some noise that is generated inside these devices. There might be some stray noise that gets through the concrete ceiling of the basement, and that needs to be taken into account. So what we'll be looking for is a signal that is 106.2 microwatts per meter squared above whatever these are currently displaying. So whatever these display in the basement, we want to, when we turn the transmitter on, to have 106.2 microwatts per meter squared above that received signal. So let's take these down into the basement now and see what their received signal is with absolutely nothing there whatsoever. Let's go and do that now. That's where the transmitter will be, and the path is across the room here over to the receivers here. But what we want to do is find out what the background level of RF is down here in the basement. So I'll turn the lights off. I've got a torch here. Let's have a look. What do we see? Okay, so the phone is now in airplane mode. So on the GQ meter we got 0.001 milliwatts per meter squared. And on the other device, we've got 0.032 microwatts per meter squared. Let's just leave that for a few moments and make sure they level out a bit. Yeah, so we're spiking about 0.005 milliwatts per meter squared here. And over here we are 0.028 microwatts per meter squared. Okay, I'm happy with that. That is, I think that's sufficiently low. We're going to be okay. So the initial test is now ready to go. That's the transmitter box there. It's got a laptop and the software-defined radio inside, and a quarter wave 869 megahertz antenna on top. On the other side we have the two. On the other side we have the two RF measurement devices we're going to test. The distance between the antennas here and the transmit antenna is exactly 3 meters. I'll just turn the backlight on here. So you can see the initial readings is as we had before when we brought them down here just initially to get background readings. So between 0.001 and 0.005 milliwatts per square meter on there, and it's sort of 0.2 microwatts per square meter on the TM-195. So I'll now go and turn on the transmitter and we'll see what we get. The transmitter is on, and the EMF-390 is giving pretty much nothing almost. And this one here is also, what do we get? Oh wow, about 1.4 microwatts per square meter. Yeah, it's not the best, is it? What happens if we turn it like that? Well, that's interesting. So now we have a bit more. Considering it's meant to be a triaxial antenna, that's not particularly impressive, is it? Okay. What happens if we move the orientation of this one? 0.0. That's interesting, considering you meant to supposedly point that to the transmitter. .22, 0.25, and there we have 0.45. I mean, they're just pretty poor, aren't they? Really. If I hold it here, there's no way we can take accurate measurements like this. It's just the devices are so bad. It's just not going to happen. Right. Well, well done. If I put these vertical here, I will go and stand the other side of the window and read them from there. Okay, so we now have the 2 meters oriented vertically, and as you see, they are way off. So the EMF-390 is it's giving us about anywhere between 0.1 to 0.15. I saw just now milliwatts per square meter, and the TM-195 is at 10 milliwatts per square meter. And that's an order of magnitude out. It's pitiful, really. Yeah. Okay, well, there we are. What I'll do quickly is I will change the frequency. I won't change the antenna. I'll just kludge it for now. And let's say go to 400 megahertz and see what happens. No, 433 actually was what we decided. 433 megahertz. Now it's 433 megahertz, and the EMF-390 has got nothing. Superb. And the TM-195 is at 11.4 microwatts per square meter. Not best, is it? What happens if we... The EMF-390, you get another decimal place if you put it on its side, it seems. Let's try that, shall we, without knocking it all over too much. There we are. Okay, so yeah, it looks like the EMF-390 isn't even receiving the 433 megahertz signal. It's back to background levels. Yeah, at least the TM-195 seems to pick it up a bit. Okay, let's try upping that to 1.8 gigahertz. So we are now transmitting at 1.8 gigahertz. That's basically GSM 1800. And I think there's 3G and various other things up there as well. And again, there's yeah, the EMF-390 doesn't actually seem to detect it at all. The TM-195 likewise doesn't seem to find that signal. It's definitely there because I just saw it. Let's just let's take one of them right next to it, shall we, and see if it picks up anything at all. Oh, just lost a slipper. So right next to the transmitter, we've got 2.5 milliwatts. Two milliwatts at about 1 meter. We've down to 500 microwatts, and then we pop down to 3 meters away. Yeah, there's nothing there. It's barely detecting that signal. Let's do the same with the GQ. So, GQ EMF-390. This is basically transmitting a GSM signal now. At that frequency, it's a... so right next to it, we're managing to pick up a little bit. Okay, oh dear. Okay, right. Well, let's try Wi-Fi, 2.4 gigahertz. So I'm transmitting a Wi-Fi signal on 2.4 gigahertz now. It actually looks like Wi-Fi. It is a 16 QAM signal fed with a random byte stream, and yeah, not much there at all. So I hope you've enjoyed this fun video looking at these two plastic bits of tat. Yeah, they're not particularly good, but if you like the video, if you got some more of these you want me to try out, then let me know. Put them down in the comments. If you have links, even better. If you want to send me one to test out, I promise to look after it. Oh dear, it's beeping again. Oh, I promise to look after it and send it right back to you as soon as I've done a video about it. But yeah, if you like this, then don't forget to subscribe and like. And there's a little dingy bell thing down there which will alert you when I send out new videos. Happy New Year again, and see you soon.